All right, how's it going, everybody? We are here on Thursday, February 18th. We're going to talk about section 7.4 today. We're going to get partial fraction decomposition, or PFD for short, since this is a really long phrase right here. Another integration technique that we're going to get that's going to help us out, mostly with our rational functions that we're integrating here. So today we're going to hit 7.4. Next section, we're going to hit 7.5, which is a pretty generic section on strategies for integration. And I'd just like to point out kind of like why I think that's kind of a special thing in this book. In this book, I think there are, out of like something like 17 chapters in this book, there are a grand total of only two sections in the entire book that are essentially like review sections, and this is one of them. And it's because there's a lot of stuff that we've learned here. And so I do think it's important to stop and sort of summarize the things that we've seen. And so you should like stop and take a moment to acknowledge like the importance of the book being like, dang, we got to stop and summarize some of this stuff right here because this has been a lot as far as our different integration strategies go. Integration by parts are two different trig sections. This partial fraction decomposition here. We've learned a lot of different ways that we could potentially approach performing integration. And so in this section, it's going to sort of say, let's stop and like think about all these together and kind of like take a step back and see some kind of bigger picture things about why integration is hard and kind of a order of, in a sense, like an order of operations. Like what's your checklist that you're looking for when you're performing integration as to saying, okay, should I try a U sub? Should I try integration by parts? Like what's our natural ordering to that? So that's what we're going to look at there in 7.5. So let's go ahead and hit it with some partial fraction decomposition. So again, today is going to be all about rational functions that we're integrating. And the point of this here, our big idea is that simple rational functions, by which I mean rational functions that have a linear denominator, are really easy for us right here, right? We've got these two examples that are sitting right here. Our first one, 1 over x, this is just our like absolute baseline linear function right here in the denominator. We know this is going to be giving us our natural log of x plus c, right? So we're expecting today to get lots of stuff that's going to look like natural logs because of the fact that we're going to be integrating lots of rationals. But the point is, these are only easy when we have this linear term in the denominator, right? Here we could do a little bit of a u sub if we still need to write this one out. This u sub's really only handling a constant multiple for us here, so it's nothing too crazy. If you could do this one in your head, I'm cool with that. But it looks like here we're getting our integral of 1 over u, 1/2 the integral of 1 over u du, which is giving me 1/2 natural log of u, which is giving me 1/2 natural log of 2x plus 5 plus c, right? So those are our easy ones here today. Obviously, those aren't the ones that we're here to talk about. This is our motivation to say when we see things that are not simple rational functions like these with linear denominators, our goal is going to be to take out our algebra beating stick and force these things to have those nice, easy denominators that we want. So today, as with all days of this class, the challenge is not in the calculus, the challenge is in the algebra. I know that you guys have been feeling that over the last couple of weeks here, and that will continue to be the case today, that we're going to say, we're not going to do any hard integration. We're going to do hard algebra to make the integration easy. So this should be the level of difficulty right here of the hardest integration that we're doing today, is doing these steps right here. The difficult part is going to be algebraically manipulating our integrands until they're this simple here. So again, this is our hardest calculus step here today. The algebra is what we're here for. So when we see rationals with more complicated denominators down there, maybe meaning not a linear denominator, what we want to do is find some way that we can rip apart these denominators so that they do have some linear terms in the denominator, so that we can go ahead and do that easy integration step right there. So with this guy here, let's do our first partial fraction decomposition. And by the way, in the textbook, this is, if you go to the problems for section 7.4, this is problem number 3A right here. So here's my deal with this guy. There's two things that I see right away that I'm thinking about with this integral right here. One, I see that we have a constant multiple of 2, which that pretty much never does anything for me, right? I pretty much always just pull my constant multiples out front, my integral here. The other thing that I'm seeing here is that when I see this quadratic in the denominator, my instincts tell me to do quadratic things with quadratic stuff, right? Here, what I'm seeing to myself is this looks like something I think I could factor, right? X plus 4 times x minus 1, I think is our factored form for that guy right there. And getting into this factored form is something that's sort of essential for my partial fraction decomposition process. Or I should say, it's not required, but it's definitely something I'm hoping that I can do. What you should notice now is that we now have an expression that looks like it's got two different linear factors in the denominator rather than one quadratic factor. In a sense, this is closer to what we want because our goal is to just have a single linear factor in a given fraction there. Right now we have a product of two of them. So it's still really, it's like a quadratic down there, but we've made it look like it's two linear factors. What I know is that anytime that I have a product of two things in a denominator, what that kind of feels to me like is it seems like it's the result of adding two fractions together that didn't have like denominators. You know that if you add something like 1/2 and 1/3, that you need to multiply 1/2 by 3/3, you need to multiply 1/3 by 2/2, then you'll have common denominators of 6 and you can add them. It seems like that's a situation where we've already arrived at the common denominator of x plus 4 times x plus 1 because we added two fractions together. My question to you is, can we figure out what two fractions we might add together that have the individual denominators of x plus 4 and x minus 1 to arrive at the collective denominator of x plus 4 times x minus 1? And so our algebraic goal here today is to do that algebraic ripping apart. I want to rip apart this fraction that has a product of two linear terms in the denominator to instead being two fractions that are added together that have a single linear denominator term. So here is what I want. Switch here to blue. And I'm going to say what I want is I want to find some way, and now we're just doing algebra here. I've got no integral signs here. I'm just algebraically manipulating our integrand here. What I want is I want to find some fractions that have x plus 4 as one of the denominators and as x minus 1 as the other denominator. This is sort of my goal structure for this thing right here. The whole point is I don't know how much of this fraction I need to add to how much of this fraction to make that happen. So I'm just going to go ahead and identify some general variables a and b that might do that for me here. And today we're going to talk about how do we know how to make our special choices of a and b. What should our numerators look like, that kind of stuff. We'll see those in a couple examples coming up here. So our goal today, though, really, like the meat of the math that we need to be able to do today is to say, can you solve for a and b? And I want to immediately tell you, you should be nervous about your ability to do this. Why? Because right now what we're looking at is an equation that has, and by the way, x is like a true variable here, but what we're trying to solve for are a and b. That's what I want to solve for in this case right here. And the important thing that you should recognize is that we only have one equation, but we have two unknowns. What you should have learned in algebra class is that that's not enough information to make this happen. We're going to see some special things that are going to show us that this actually is enough information to happen in this case right here. So here's what I want to do. When I look at this equation right here and I'm trying to solve for a and for b, what I'm saying to myself is, man, this is a crappy equation because everything in it's a fraction. Let's get rid of all the fractions. And the way that I'm going to get rid of all the fractions is I want to multiply the entire thing by this denominator over here. So what I'm going to do is I'm going to multiply the entire expression by x plus 4 times x minus 1. What that's going to leave me with is on the left-hand side, I'm only going to get 1. All right, I cleared the fraction there. I multiplied by x plus 4 times x minus 1. On the right-hand side, I'm going to see that when I multiply by this product of these two factors right here, the x plus 4 is going to cancel on the fraction with the a component, but the x minus 1 is going to survive. So I'm going to get an a times x minus 1. Similarly, for the b factor over here, the x minus 1 is going to cancel with the x minus 1 that was multiplied through, but the x plus 4 will survive. All right, so here's my really important algebra steps. Again, we have one equation, but two things we're looking to solve for, a and b. And so again, every algebra thing you learn should say to you, I don't think we can do this, but let's look and see how these components break down. What I don't want is I don't want to group these things by how much a do we have and how much b do we have. Instead, what I want to do is I want to say how much x stuff do we have and how much constant stuff do we have. So what I'm going to do is multiply these out, ax minus a plus bx plus 4b. And what I want to do is I want to group together my x components, that's the ax and the bx, and I want to group together my constant components, that's the negative a and the 4b on this right-hand side here. So how much x stuff do I have? I have a plus b of it, right? There's ax is there, there's bx is there for a total of a plus b x's. Similarly, how much constant stuff do I have? I have 4b minus a as my constant term right here. There's no x's involved. X is my variable. There's no variable x associated with the negative a and the 4b, so I have lumped those two guys together. What we can now do is we can now do what's referred to as matching coefficients. And the deal with this is I know that if I have some amount of X stuff, that can only be made up by other amounts of X stuff over here. Oh, I'm sorry, I'm falling off my side over here. There we go. Now I'm not falling off anymore. All right, we'll leave it right there. So there we go. Now I've got it all on screen here. So the point is I'm going to do what we refer to as matching coefficients. And what that says to me is however much X stuff I have on the right needs to be however much X stuff I have on the left, which notice is 0. However much constant stuff I have on the right is going to need to match up with however much constant stuff I have on the left, which in this case is 1. There is some constant stuff. Furthermore, if there was like a quadratic term here, if there was like an x squared over here, then however much x squared stuff I have on the right needs to match up with however much x squared stuff I have on the left. So notice what this is allowing us to do is it's allowing us to write multiple equations from the one equation. So the one equation that I can write is I can say, I want to match my x coefficients on the right with my x coefficients on the left. And that's going to tell me there's 0x on the left, and there is a plus bx on the right. So it must be that a is equal to negative b. It's got to be the case. Right. The other thing that I'm looking at here is I'm looking at the fact that there is a constant of 4b minus a on the left. And it looks like that is associated with, I'm writing this weird here, a constant of 1 on the left. Sorry, 4b minus a on the right and 1 on the left. I've matched the constant terms to the constant terms, and I've formed an equation for each of them. So you should now notice I now have a system of 2 equations, right? Now we can solve a system of 2 equations to determine what a and b are. Once I know what a and b are, that will give me now a rewritten version. This is our original integrand right here. I'm going to get a rewritten version of our integrand that actually has a sum of 2 rationals with linear denominators. We can easily integrate this stuff with the a and the b. We have no idea how to integrate this stuff with the quadratic and the denominator over here, right? So that's our move right here. So let's go ahead and solve this system. I know that a is the same as negative b. So I think I'm going to kind of come to this equation right here. 1 equals 4b minus negative b, right? I've swapped out a for negative b. I did a substitution based on this. It looks like 1 is equal to 5b, and it looks like b is going to be 1/5. And if b is going to be 1/5, then it looks like that's also going to tell me that a must be negative 1/5, because a is just the negative of b right there, right? So this is good. So it looks like we have solved for what a and b are. And so I think that I can come back now to my integrand. I now have a way to rewrite my integrand as the sum of 2 rationals with linear denominators rather than a product of 2 linear denominators. And this is good for us for our solving here. Therefore, 1 over, and what did we have here? X plus 4 x minus 1 should be the same fraction as negative 1/5, that was a, over, let me make sure I got these in the right order right here. Yeah, a was what and by the way, you'll have to do this. Double check what variables were attached to what denominators here. I forget every time. Got to look back up at the original part of my work. A was associated with the x plus 4 factor. A was negative 1/5, and it's got that denominator of x plus 4. The other one that we got is positive 1/5. And that was associated with the denominator of x minus 1 right there. So the whole point is our integrand currently looks like this, but we have just found that we can rewrite this fraction as the sum of these 2 fractions, which are way easier for me to integrate here. So now I'm going to go back into integral land here, and let's see if we can do this guy. So we've now got our integral 2 times our integral. Remember that let me just scroll back up here. That 2 came in our numerator right here. I pulled it out front. By the way, 2 could have totally been left inside right there. I could have had this 1 be a 2 this whole dang way right here. We would have ended up finding 2/5 and negative 2/5. That constant multiple of 2 is either going along for the ride in the partial fractions, or it's going along for the ride outside of the integral right there. Either one would have been totally fine. So I've got 2 times 1 over x plus 4 times x minus 1 dx. We're going to say that that is equal to 2 times, I guess I don't need that yet, but I'm going to use that parenthesis in 1 second here. 2 times the integral of negative 1/5 over x plus 4 plus positive 1/5 over x minus 1. And what I'm recognizing now is I can easily rip this apart into two separate fractions, or two separate integrals right here. We've got constant multiples. Notice, by the way, and notice another thing that I'm doing that should feel really weird to you right now. You should be saying to yourself, why is Tony leaving this as like a mixed fraction like this? It's because this is just a constant multiple of like 1/5 and negative 1/5 that I'm going to pull out front of the integral. The last thing I want to do is make this like 1 over 5x minus 5. That's going to make this harder to integrate, not easier. This is a constant factor that I am totally comfortable with just pulling outside of an integral. So that's why I'm not like simplifying this fraction into a nicer form. I have no reason to do that, right? So what I'm thinking here is this. 2 is going to multiply two integrals in a second, which is why I'm opening up a parenthesis. The first integral has a constant multiple of negative 1/5 in the numerator, which I'm going to pull out in front. And that's leaving me with just a 1 over x plus 4 dx. The second integral has a positive factor of 1/5 that I can pull out front, which I'll do. And it looks like this is a really easy setup for some integration right here. So I am seeing here, it now looks like I can distribute this 2 back through and get something that looks like negative 2/5. That's my first one. The integral here is very easy, natural log of x plus 4 plus 2/5 natural log x minus 1. Hey, that worked out pretty nice right there. I should give myself a plus C because I'm a responsible mathematician. And I do just want to show you one last thing that we can do to kind of combine our answers a little bit here. You guys know that addition and subtraction outside of a natural log should result in multiplication or division inside of a natural log. I'm pretty cool with this being a version of a final answer, but I don't think it's uncommon at all to see people simplify this by combining some things. I think here's the way that I would rewrite this. I don't like seeing negatives first, so I'm going to switch the ordering of these two terms, like the second will become first and first will become second, just to rearrange the order. I'm also going to factor out the 2/5. So I'm going to write this as 2/5 times this term first, natural log of x minus 1, minus this term here, natural log of x plus 4. And this I can now write as 2/5. These two terms I can now combine because they are just single natural logs right here by subtraction. Subtraction outside the natural log says division inside the natural log. So this will look to me like natural log of x minus 1 over x plus 4 plus c. And I think that this is our kind of most compact final answer right here using our properties of logs. So pretty cool. So the cool idea here is we don't know what to do in this first case right here because we're a little bit stuck with that quadratic down there. And by the way, I kind of want to point out something. I guess I kind of glossed over at first, but another thing I think to myself when I see stuff that looks like this is it's like I want to do this u sub right here, right? That's like what my instincts tell me I should do. But the whole problem is when I go to get my du, 2x plus 3 dx, like I don't have any x multiple times the dx, right? If that was a straight up 2x right there, I'd be in a lot better shape to do this just by a u sub, but we don't have that, right? So it looks like this guy, like doing that u sub doesn't work. We don't have the components we need in the numerator to make it happen. So instead, we factored the quadratic. We did partial fraction decomposition to rip apart the denominator from a multiplication of two factors to a sum of two linear rationals. The linear rationals themselves are very easy to integrate. This is as hard as our integration actually was right here. The algebraic challenge was getting there, right? So now that we've done one, now I'm going to be responsible and say, hey, you should stop for a moment and practice one on your own right now. So if you're watching this video not live, you should pause the video and give this guy a shot right here. You should notice, the question that I'm seeing in chat right now is, I'm going to say my thing real quick, and then I'm going to answer your question right here because it's a good one. So evaluate this integral right here. You should see that denominator of x squared minus 1, you can factor that. That is a factorable quadratic as x minus 1 times x plus 1. So you can perform your partial fraction decomposition. You should notice that this one does have bounds of integration of 2 and 3 right there. So this is a definite integral. And if you do a bunch of your simplification, your log simplification like I did here, you should end up at an answer of 1/2 times the natural log of 3/2. You should then, as we have done in the last couple sections, go type this integral into Wolfram alpha and feel the disappointment that it doesn't quite do the same things that we want to do right here. So you should stop and do that right now. Now, the question that I'm seeing here in chat is, would completing the square also work for this? And the answer is yes. What you guys should have seen in our week 5 written homework is I'm asking you to do a problem that looks very similar to this one as the second problem, but I'm suggesting to you to complete the square and then do a trig sub on that guy right there. So that is kind of our two routes that we can take whenever we have, for example, a quadratic rational function here, is we can either complete the square and use the square plus or minus a constant to use a trig sub associated with that one. That's one thing we could do. A different thing that we could do is if it's factorable, we could factor that quadratic and we could use partial fraction decomposition to rip it up and go this route. Both of them will lead you to exact same answers. But it's really, and I like these two techniques going hand in hand like that, because it's like those are the two things that we've learned to do with quadratics. You can factor them or you can complete the square to get them into more useful formats. Both of them are more useful than standard form for the quadratic in this case. One leads you to a trig sub solution, one leads you to a partial fraction decomposition solution. In my opinion, I feel like I'm more comfortable doing the partial fraction decomposition because this is just algebra. Bringing trig into things is always, I think, for most of us, slightly less of a confidence zone right there. There's nothing wrong with it, but the point it was with our written homework for week 5, I asked you to do this by completing the square. And in the week 6 written homework, we'll see, I'm going to just give you that exact same problem from week 5, but I'm going to say do it with partial fraction decomposition, make sure that your answer matched the one that you got the week before, to see that we can do these both routes right there. But the bottom line is kind of saying to me, like, when is it ever, gosh, all I want to do is, there we go. When is it ever useful for us to have quadratics in standard form? And the answer is rarely. We really like factored form and vertex form as our more practical formats for quadratics, and both of them are better than standard form in this case right here. Cool. So stop and do your little practice one right here, and then we'll move on. And what I want to say here is this, going into our next example. The reason that the above example, this one that we just did right here, worked out so nicely is because we had distinct linear factors. And what I mean is there's two different things right here. When I say distinct, what I mean was we did, when I say distinct, what I mean is we did not have two repeated factors, right? That wasn't like x minus 2 times x minus 2. The other thing was that the factors that we were able to break it down into were linear. It was just the x minus 1 and the x plus 4, right? We didn't have to factor it into like a quadratic times a cubic, and that was the best we could do. So the two nice things that happened here were, when we factored our denominator, it gave us two linear factors, and those linear factors were different from one another. Those are the two nice things that are subtle right here that weren't obvious. So what we want to kind of talk about real quickly here is what happens if our factors are not distinct? What happens if there are repeated factors? The other thing we want to look at is what happens when our factors, that when we decompose this as much as we can and factor as much as we can, what happens when those final like baseline factors aren't linear? Those are two slightly more complicated things that we want to discuss. Let's talk about each of those guys right now. So the first question is, what happens when we get repeated factors? Meaning, what happens if this was like an x minus 2 cubed? That would be 3 repeats of the factor x minus 2. Those are therefore not distinct factors. They were repeated factors. So example 4b in the book, I'm not going to do the integral of this. Let's just state what the partial fraction decomposition should look like if you were going to do this. I will never ask you to do one that's quite this large right here, but we should at least be able to state what would we set up for this guy right here. Ultimately, some of these turn into problems that are probably better phrased as linear algebra problems rather than actual just algebra problems where you should probably solve them with a matrix instead. We won't go quite that far in here, but it's technically something that might ever crop up right here. So in general, for this guy right here, what you should importantly be seeing is that we do have these repeated factors, right? A repeat factor of x, a repeat factor of x plus 3. So what I would be setting up here for my decomposition is saying x squared plus 1 over x cubed times x plus 3 squared. What we're going to want to do in this case is we're going to want to introduce a new term with like an unknown. And by the way, it's just standard convention. I don't quite know why. It's standard convention to use capital letters right here when you're doing your partial fraction decomposition. I don't know why. As you know with math, there's sort of just these like, so, a fat white guy decided that 400 years ago, and therefore that's what we do now. That's just a typical thing. You know, learn to expect that right there. It's very common variable selection right there. So what we want is we want one of those capital letter parameters for every one of our possible factors that we have in the denominator. And what I mean by that is, since there is, in a sense, a factor of just x down there in the denominator, I do want an a over x. But we could also think of this as having a factor of x squared down there. And so we're also going to get a b over x squared. We could also think of that as having a factor of x cubed in the denominator. So we're going to want to introduce a term for that as well. And then similarly for the x plus 3 terms right there. We could think of that as having a factor of x plus 3 to the first. We could also think about this having a factor of x plus 3 squared right there. But notice the nice thing here is that each of the, if you just strip away the power on the entire denominator, all 5 of those terms are linear. It's just x's and x plus 3's collectively to powers right there. This obviously is going to take you quite a bit more work to solve than it did just to get our a and our b before when you have 5 constants right here, but the technique would be the same. We would multiply both sides of the equation by the entire left-hand side denominator, and we would attempt to match coefficients. We'd say however much x squared, and notice by the way, the only thing we have on the left numerator is x squared and 1. So it should be that if we get any terms over here, notice that we're effectively multiplying by like an x to the 5th something, right? So all of these terms are going to have as much as like an x to the 4th attached to them, but there's no x to the 4th, so all those coefficients would be set equal to 0. There's no x cubed, so all those coefficients would get set equal to 0. There's 1x squared, so all the x squared coefficients over here would get set equal to 1. There's no x components, so all of the x coefficients collectively would get set equal to 0. And there is a constant of 1. So any constant coefficients over here would get set equal to 1. That would give you a system of 5 equations, 5 unknowns, not something we want to be doing by hand, but something we technically can do by hand right there. Right? So in any event, the point here is when we decompose these, if you have repeated factors, like there's 3 repeats of x and like there's 2 repeats of x plus 3, you need to introduce one partial fraction decomposition term associated with all possible integer powers that you see up to the highest power that's out there. That's our appropriate way to decompose this guy to get all the terms that we might need. So now what we want to look at, and by the way, I'm also going to show you in a second here, once we summarize this, we're going to do one more example and then kind of summarize what we've seen. And one of the really nice things that goes along with this technique right here is that if you forget some of these rules, it turns out that it doesn't really matter. And I'm going to show you what I mean by that coming up here in a minute, but we'll talk about that in our summary in a second. All right. So what our sort of worst case scenario here is when we have denominator terms that we just straight up can't factor into linear factors, right? Our best case rational function is one with a linear in the denominator, but we can't guarantee that every like quadratic is going to be factorable, right? So sometimes you're just stuck with that stuff down there. In those cases, I'm going to say we need more than just an unknown constant in the numerator, right? We're not just going to get just capital A in the numerator in those cases. So let's go ahead and take a look at our next example here, where we're not quite going to be able to break it down as far. So in this guy right here, we've got a quadratic divided by a cubic here. So what I'm seeing here is as soon as I see this denominator that seems slightly factorable to me, I'm saying to myself, ooh, maybe I can make something special happen with this x cubed plus 3x right here. Let's see if we can factor this guy. If I try to factor this, then what I'm getting is x times x squared plus 3. And the important thing to notice here is that I have a quadratic factor of x squared plus 3. I have nothing else I can do with that, right? There's no further decomposition. And it's not even like if that was x squared minus 3, I could at least factor that as like x minus square root of 3, x plus square root of 3. It would be a pretty big bummer that there would be square roots being introduced, but I could do it. I have no way of factoring this without introducing imaginary numbers, and I don't think imaginary numbers should end up in our answer if we have a real valued initial problem right here. So it doesn't seem like there's any factoring that's reasonable for me to do in this case. So what we want to do is we want to go ahead and do our partial fraction decomposition still, but we're just going to say we need a little bit more than just a constant in the numerator whenever we have a nonlinear denominator term over there. So here's what we're going to do. We're going to get here x squared minus x plus 6. This is the thing that we want to decompose. What I would really like to have is a denominator of x and a denominator of x squared plus 3. And notice that this is, by the way, not a repeated factor because there's only one copy of the collective factor. It's true that one of the terms is squared, but the entire factor itself is not squared. It's not a repeat of the entire factor, right? So what we're going to do here that's ever so slightly different in this case is, since x is a linear factor, it does just get a constant, an unknown constant as its numerator like before. Since this is a quadratic that we can't break down any further, it's going to get a one-dimensional lower, or one degree lower unknown in the numerator. So 1 degree less than quadratic is linear. So what I'm going to give right here for my numerator is a bx plus c. All right. We're going to need potentially for that b term to be there, an x component in the numerator to help make everything agree with the possible outcomes associated with our partial fraction decomposition here. So that's going to be our kind of general rule here, is if you get down to a factor that's not linear and you can't factor it anymore, then you need a 1 degree lower polynomial as your unknown up in the numerator up there. So quadratic, 1 degree lower than degree 2 is degree 1, so a linear unknown up in the numerator up there. Now let's go ahead and see if we can determine what a, b, and c are so that we can proceed with our integration right here. So I'm going to multiply this whole thing by x times x squared plus 3. In doing so, I'm going to get an x squared minus x plus 6 equals, again, x cancels with x on the a component, but the x squared plus 3 is still multiplying a. Alternatively, bx plus c, this fraction that's right here, when we multiply through by this entire denominator to clear the fractions, x squared plus 3 cancels with x squared plus 3, but this x is still multiplying bx plus c. Now you should notice I actually kind of did this a little bit weird in that here I had the constant a, and then in parentheses the multiplier. Here I had the multiplier x, and then in parentheses the numerator bx plus c. That's cool with me because I know that what I'm not interested in doing is grouping these by a's and b's, but grouping these by their how much x stuff they have in them. So notice over here we have x squared, we have x, we have constant. Those are the three groupings that I also want to make on my right-hand side. I'm asking on the right-hand side, how much x squared do we have? How much x do we have? How much constant do we have? That needs to agree exactly with the left-hand side because you can't just take constant multiples of x stuff to get x squared stuff. The only way you get x squared is with x squared. And so however much is on the left has to be exactly however much x squared is on the right, etc., etc. So let's do that here. So x squared minus x plus 6. I want to expand this guy. Ax squared plus 3a plus bx squared plus cx. So what I want to do is I want to write this in terms, I want to rearrange this so that this basically looks like it's in standard form for a quadratic here. So it looks like how much x squared stuff do I have? I have a plus b x squareds. Next question, how much x stuff do I have? Well, there's only one x term here. It's a plus cx. Final question, how much constant stuff do I have? I have 3a is my only constant term on the right. And so, and just to make sure that we're all clear here, use some colors. Make sure everybody can see what we got going on. Don't forget your negative on that guy right there. All right, so we're going to get the equations of 6 equals 3a. That's one equation. We're going to get the equation of, it looks like negative 1 equals c. That one's easy. Done with that one. And notice like that kind of happens a bunch with these things. So just even if you see that you need like, five letters or something, like three letters that we're solving for here, it's not uncommon for some of them to be like trivially easy for you to identify here. And for our final one, there's 1x squared and there's a plus bx squared. So we're going to get 1 equals a plus b here, right? So this looks pretty easy in that, like one of them's done, right? There's one of them. One of them's essentially done, the green one. We've got that a looks like it's 2. And using that, I guess I should say, now I'm going to plug that guy in over here. And that's going to lead me to be able to say what we get for b. It looks like 1 equals 2 plus b. And therefore b is going to be -1. So that was actually a really easy system to solve once we'd set up our appropriate groupings out there, right? So again, matching coefficients is an awesome thing that we can do, this awesome technique where we can just say, listen, since this is clearly a quadratic on the left and a quadratic on the right, I know that the coefficient on each of the matching terms from left to right have to be equal to each other, or else we don't get equality right here. So instead of grouping by a's, b's, and c's, we group by x squared, x, and constants, and that allows us to build 3 equations, which helps us solve for our 3 unknowns. So we have done our partial fraction decomposition. We know exactly how this grosser fraction decomposes into 2 nicer fractions. And I say nicer, I don't necessarily mean nice because it looks like we still have some work to do with our second term here, but this is at least going to lead us towards something that we can actually handle now. So let's go ahead and do this here. And I do think I actually want to just kind of, yeah, I'm just going to use my extra room right here. So it looks like we're saying now that we're going to be able to rewrite this as the integral of, and now I'm just using the terms that we just solved for here. So we found that a was 2, so it looks like it's 2 over x, that's my first term, plus, and what do we get here? -1 for b and -1 for c. So maybe I can just call this, here's what I'm going to do. Well, okay, no, I'm not going to introduce any confusion right here. I do plenty of that, I think. So we're going to get a -x minus 1, looks like our numerator for the second term, with the denominator of x squared plus 3. So that's what our decomposition told us. That's my 2, my -1, and my -1 that we solved for. Right, that's right there. Let's go ahead and see, can we do this integration now, is the new question here. So I'm seeing some things here like, one thing I'm seeing is constant multiple of 2, that gets pulled out front. Constant multiple of -1, that should get pulled out front. 1 over x, that's an integral I can easily do. So I think I want to do these 2 integrals separately. Not quite sure what we're doing up here, though. We're going to have to maybe do a little bit of work right there. So let's go ahead and say it should be equal to 2 times the integral of 1 over x dx. That one's easy. I'm done with that one already. Done right there. I'm good with this part's completely handled. Our other component here, I'm going to do a minus. So that minus is me factoring out the negative from the numerator right there. And I'm going to write this as x plus 1 over x squared plus 3 dx. And now the question is, can we do this second integral? Well, I can't do any more like partial fraction decomposition type of ideas because x squared plus 3 is nothing that I can actually factor, right? So I can't like do more of what we've been doing. One thing I do see that I think is at least nice is it seems to me like since we have a sum in the numerator up here, it seems like we can rip apart that numerator into 2 different fractions again. So I think I can do something like minus the integral of x over x squared plus 3 plus 1 over x squared plus 3 dx. And here's kind of the thing that I'm seeing. When I rip it apart like that, x plus 1 is 2 separate fractions, I'm seeing now that if I did a u sub on this first one here, with u being x squared plus 3, I will have this x dx as part of the u sub components coming out. So I think I can do this guy right here with just a u sub. That's good to go. The other thing that I'm seeing here is this looks an awful lot to me like an antiderivative that you are supposed to know, but that I'm assuming 90% of us have all forgotten. But I'm going to remind you of it right now, since it's one of the most forgettable ones I think from Calc 1, and I get that, and so I'm gonna help you out with that one right here as well. So what do we got? Yeah, good call right there. We got one person in chat that remembers. Gold star for you. Um, so what am I doing here? I'm going to break this up into two fractions and then deal with two integrals and then deal with them separately here. So notice this negative, I'm distributing this negative onto both of the integrals right here. And here's the two moves that we want to do with these guys. For our first integral right there, it looks like we want to do something like u equals x squared plus 3, du equals 2x dx. I only have a 1x, so I'm going to move that 2 over. And it looks like that's going to be good to go for that integral right there. So if I'm kind of doing the ones I've already got, then it looks like we're getting... This is just going to now turn into 1/2 1 over u du. And getting back into x, this u was really x squared plus 3. Right? So we've got 2 out of the 3 components. All we got to do left is this guy over here. And so now I'm saying to you, oh, you should stop and think about this one. And again, for all of you that are watching this video after the fact, maybe right now is a good time for you to pause and to go look in the back of your textbook, in the very back cover of your textbook, and see if you can figure out what this is supposed to be, what you're supposed to recognize. And here is what you are supposed to be able to recognize here. I think maybe this is our derivative to remember here. Right? There's the derivative that you learned in Calc 1. The derivative of inverse tangent is 1 over x squared plus 1. This looks really, 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 really similar to that. You will see in the back of your textbook that we get the general form of 1 over x squared plus a squared dx equals 1 over a tan inverse of x over a right there. So that's the general form that I'm using here. You should notice that we have a is the square root of 3, right? Because it's not really a perfect square, 3, unless you are okay with square roots, then it is a perfect square. It's a perfect square of square root of 3, right? So it looks like from this guy right here, we're just going to be getting out some inverse tangent, give or take some constant multiples because of that 3 right there. And so I'm going to just kind of, I think I've just got this one right here. This is just going to be minus, what is it? I'm just following this format right here, right? 1 over root 3 tan inverse of x over root 3. Right, just following my given format for that guy right there. That's based on a derivative that you learned. So this is one of those ones that I kind of consider to be like on the fringe of stuff that I actually expect of you guys. Yes, when you see a 1 over x squared plus a constant, I absolutely expect that you remember that that's somehow related to trig something. And I fully expect that you're capable of looking it up and using the general forms of some integral formats like that to figure out how you would get an expression for this one. Again, this is not one that comes up crazy commonly, but like when I look at this, I mean, that's how it went for me is I looked at that and I was like, oh, that's like one of my inverse trig functions, right? That's what I remembered from that. I can't even say for sure if I remember. I'm pretty sure I remembered as tangent because I know that sine and cosine have the square roots in the denominator term down there. But I didn't remember exactly the structure of where I knew that there was a's as coefficients and stuff. I forgot if they were multiples or divisions and stuff like that. And I went and looked it up and I used the general form that I found out there. So yeah, you should be able to come up with these guys right here. It might be that you need to glance at your reference in the back of the textbook. That's acceptable. I expect that you see that and say, I feel like that's one of my inverse trig functions right there. And it is, right? So looks like we've got our good final answer for this guy right here. Nothing else we can really do with this to simplify this any further unless you really wanted to combine some natural log terms, which I don't. Combining these natural log terms, then we'd be getting like natural log of x squared over the square root of x plus 3. That's technically possible. You know, what would this look like? This would look like something like a natural log of, right? 2 would be the power on x, so we'd get like an x squared over 1/2 being a power is like a square root. So that could be like an x squared plus 3 is under a square root right there, something like that. Minus our 1 over root 3 tan inverse. And these are just useful like things to be able to do because if you are like checking your answer in the back of the book, Wolfram Alpha, whatever, it might be giving you stuff in this format, and it's important that you recognize that these are like the same thing as each other right here. I certainly don't necessarily expect that you like mash together every single natural log term. I think either one of these to me is good for a final format for an answer right there, I guess is what I'm saying. So there we go. So again, strategy wise here, because we had an irreducible quadratic, we had to use a bx plus c term instead of just like a b up in the numerator up there. We matched coefficients, and honestly is even easier than the previous example. We didn't even have to this is barely solving a system of equations, right? But it led us to something that wasn't directly obvious with what we could do right here, but by further separating into more and more fractions, we were able to recognize that one was handled with a u sub, one was handled with an inverse trig antiderivative, and we were done right there, right? So it broke down into 3 integrals that we handled differently. Direct easy antiderivative, u sub, slightly harder direct antiderivative because it's an inverse trig function, but all 3 of them came out pretty nice right there. Cool. So let's kind of summarize what we've seen, and then let me tell you a very nice kind of thing that's going on here with these guys. So the goal or hope whenever we're seeing these rational functions is that we can factor the denominator into all linear, non-repeated factors. That's your easiest case scenario. That's when the integration is just directly straightforward once you've decomposed, like our first example. And in those cases, we can always just give a constant parameter for each numerator, right? So when I say constant parameter right there, I just mean like A, B, C, etc. Right? If we get repeated factors, then we need to include a fractional term associated with each grouping, right? A over x plus b over x squared plus c over x cubed, something like that. So that's saying account for each of the possible factors that we could break it down into. All of them need their own special term in there. If we get factors that can't go into linear factors, like x squared plus 1 or the x squared plus 3 up above, then the numerator should be an unknown of 1 degree less than the denominator. If we had an irreducible cubic in the denominator, then you need to have an ax squared plus bx plus c as your numerator up there. You've got to have a 1 degree lower numerator as your denominator. Finally, this is the bullet point that's my favorite part about this whole dang thing right here. If you aren't sure what you need for parameters and you're saying to yourself, wait a minute, can that one just be A or does it need to be an AX plus B? I can't remember. The awesome thing is that you can just throw in extra parameters out there, and if it turned out that you didn't need it, you'll just solve for it to be 0, and it will just not end up being in your final decomposition. So I do this with myself all the time because I forget my rules associated with partial fraction decomposition when it comes up, and I always do this thing where I'm like, wait a minute, don't I need that one to be like an AX plus B? I don't remember. Or can that one get away with just being A? I'll just say to myself, screw it. Just make it AX plus B. And then half the time, it turns out I didn't need that X term up there. So the A term, when I solve my system, ends up being 0. So I get a 0x plus B, and B is the only thing that survives. So the cool thing here is that your broader strategy with this can really be, there's no such thing as having too many terms. If you introduce terms that weren't really necessary, you will just find that they are equal to 0, that the associated coefficient is equal to 0, and you won't actually have it in your final format. The only risk is you don't do enough terms, right? So if you don't do an AX plus B when you needed it, then you're not going to get any kind of decomposition that's going to end up working out for you out there. So this says if you're ever unsure and you've forgotten your rules, just throw it in. Just put that thing that you're wondering if it needs to be there in. If you end up solving for it to be 0, then that just meant it could have just never been there and everything would have worked out just fine. So it's saying you're safe to do too much. You're just not safe to do too little right here. So err on the side of caution. Include a term if you think it might need to be there. If it didn't, you'll just get 0 for its coefficient, and then it's not there like it wasn't supposed to be. So this is sort of the thing that says if you forget your rules, that's cool. Just be safe. Include every possible term that you think you might need, and everything will work out nicely. So this covers all rational functions with a degree of the numerator. So now let's look at one more little caveat here. All of our examples so far have had a numerator of lesser degree than the denominator, a proper fraction. However, if you don't have a proper fraction, if the degree of the numerator is more than the degree of the denominator, then you can do a little bit of long division to convert it into a polynomial. not a rational, plus a proper rational where the degree is less than or equal to, the numerator is less than or equal to that of the denominator right there. Um, I'm not going to do an example one of those right now, but you should go look at example 6 on page 501 of the textbook, and they'll do one of those examples where they say, oh, look, it's a cubic divided by a quadratic. Our first step should be to handle that and kind of like pull out some terms, do a little bit of division to get a polynomial term, and then a proper rational. The proper rational we can then do partial fraction decomposition on. Obviously, the polynomial, that'll be just a really easy integral right there. So this is kind of one of those other things that can jam us up a little bit right here, but it's not too terribly difficult for us to kind of mitigate that situation right there, right? So again, all these partial fraction decomposition rules, they all apply to proper rationals, not rationals that have a numerator with degree greater than the denominator. So step one really is to make your rational only be a proper rational by factoring out some polynomial terms, then proceed on with your partial fraction decomposition. So let's go ahead and look at some other things that we want to be able to do here that are related to this. These are just other types of rational forms that we want to be able to handle. This is not directly rational because a rational function is a ratio of two polynomials, and a square root function is not a polynomial function. Polynomials are always whole number powers of x. A square root is a power of 1/2. So technically this isn't a rational function, but it's really close to a rational function. It gives us the same types of issues as to like how are we going to do this. Like this is something where it's like we sort of feel like it should be a natural log scenario, but that doesn't seem to quite work out for us. So the question here is, and again, notice by the way, this is a textbook problem. This is number 40 in the textbook in case you're looking for reference there. This feels to me like there should be something, I don't know. Our issue is the same. It's a rational, it's rational like, and we don't quite know what to do with it. So let's go ahead and make some guesses as to some things that we might do with this. So I want to make some guesses, and I don't want that sitting right there because I'm about to do some work right there. Some of the guesses that I want to make. Well, one thing that I'm seeing, and this is me coming hot off of section 7.2 and 7.3 with all of our trig stuff. When I see a subtraction in a denominator and a square root that's really bothering me, my first thought here is, let's hit this thing with a conjugate and see if that helps us out here, right? Conjugates can help us individually square terms by multiplying by their conjugate here. And so my question is going to be, can we like make this thing happen here with a conjugate? To multiply by the conjugate is always to multiply, since we have a sum for this term, or sorry, since we have a difference right here, I want to multiply by the same term but the sum, right? So x plus root x plus 2 over x plus root x plus 2. This is a very common thing to do to get rid of roots that exist, right? So this is going to give us x plus root x plus 2 as our new numerator. But in the denominator, I'm going to get, like, remember that this is giving us like a plus b times a minus b gives us a squared minus b squared. So the individual squares of the two terms with the minus sign between them. So the individual squares of the terms here are x squared is the individual square of the first. Individual square of the second is just x plus 2, right? And I've done the difference between them because of the minus sign right here. So the question now is this something that we can integrate right here? It's definitely the case that this is equal to now. Looks like I could rip this apart into two fractions as x over x squared minus x minus 2 plus the integral of square root of x plus 2 over x squared minus x minus 2. But the question is like, can I do this integral right here? It seems to me like I need this numerator component to not be under a square root, right? Like I don't really know what I'm going to do if I did this here. I guess maybe I'd do maybe like a u sub here. Is that going to get me anywhere with this guy? If I did this, then that would be giving me, like the integral of u over, I don't know. I don't really know what I'd do with this guy right here. I guess I could do something like, say, I could subtract 2 from both sides and say x equals u minus 2. And then I could get terms like x squared would be u squared minus 4u plus 4. So I could get like a u squared minus 4u plus 4 minus u minus 2 minus 2. Is that maybe going to work out here? Well, I kind of feel like I'm going to get stuck with this one because unless that's a factorable denominator, u squared minus 5u, I got 4, 6, and back to 4. Actually, it seems like this one might work out. It's maybe going to work this way. I think actually we could do it that way. I actually kind of thought this way was just straight up not going to work out for us right here. So this is one way. So this maybe works right here actually. I'm not going to end up completing it this way, but this is not that crazy. But this one's kind of tough in the sense that, you know, one, we hit it with a conjugate. Then we hit it with a u sub, and in fact we hit it with like the 2 version u sub where we subbed in u's, but we also subbed out some x's, and then we had to do partial fraction decomposition after doing a conjugate and a u sub right there. That's pretty dang hairy to me right here. I don't quite know that that's like the direction that I actually want to go on this guy. That seemed pretty difficult for me right there. Let's try a different something here. So the point here to me is this u equals x plus 2 right here, it didn't do as much for me as I hoped it would do. It still led me to a not quite obvious sort of double substitution right there. That still was going to lead me to more partial fraction decomposition. And all that was happening after having done this conjugate right there, which again seems like that was like 3 different steps that I did just to get to partial fraction decomposition. Not super ideal right there, right? So let's come back to our original integral here. Right. So what I'm thinking though is I feel like I kind of did see this stuff coming together. And in fact, I do think this would be an acceptable route to a solution, but like a little convoluted, not quite what I would expect you guys to be doing out there. I think there's got to be kind of an easier way for this guy right here. So what I'm thinking that I'm seeing is this. This u equals x plus 2 didn't quite do what I wanted because it still left me with sort of like an issue with the square root terms and stuff like that, right? Oh, wait a minute. I see what my issue is with this first one right here. Didn't I? Oh, I see. Okay. All right. I'm lying. I don't think this is going to work right here. Why isn't this going to work? That's still a square root of u. I'm still going to be stuck with some polynomial parts and some root parts that I'm never going to be able to sort of separate away from each other right there. So in fact, that did not help me right. I was like, oh holy cow! I was like, the whole reason I'm setting this up is to show you guys that it wouldn't be possible to go this way. And then I was like, oh my gosh, it actually is possible this way. I forgot my square root right there. That square root is going to make it really kind of impossible for us to just get like polynomial over polynomial right there. So kind of what I'm learning from this is that that square root is really my issue. It's not that it's a composition of functions, the composition of the square root and the x plus 2. That's not my issue. The issue is like the entire existence of the square root. That's really my problem. So let's make a different u sub that goes with it then. Since the whole square root's my problem, let's deal with the whole thing in one big whack right here. Now, in this case right here, like the thing that's hard about this is I don't know if I really want to take that derivative right here. It's going to introduce some difficult terms for me right here. But let's think about how else we might manipulate this. I'm noticing that if I were to do this like u sub right here, then I'm going to get to 1 over x minus u. dx, right? So it looks like the point is I still need x and still need dx. So let's solve for x and do it. So let's do this here. So what I think I could do is I can say this guy right here is going to be 3 arrows, too many right now. U squared is x plus 2. That really means to me that x is u squared minus 2. And now it's really easy for me to make this substitution, or this derivative of 2u du. Now maybe I'm in better shape right here, right? Is this the thing that I actually want this to be? Notice here, now when I go, so now I've got 1, 2, 3 equations that I'm using to make all this happen. Let's see what we end up with here. So now we get 1 over, what's x? It's u squared minus 2 minus u. What's dx? It's 2u du. This substitution should feel to you like our trig subs, where rather than getting an expression for du and having dx in it, I instead found an equation for dx and just swapped it out right there. This feels to me a little bit more like our trig subs, our sort of inside-out substitutions right there. So let's see if this is going to be something that we're actually going to be able to do. So I'm seeing some things like constant multiple of 2 is coming out front. That u is a new numerator term. In the denominator, u squared minus u minus 2 du. Is this factorable down there? It looks like this is u minus 2, u plus 1. Oh man, we're cruising now. We're partial fraction decomposition in this guy right here. So it looks like in this case right here, we made a little bit of a different u sub than we'd ever made before. My motivation to do this was recognizing that the square root, recognizing after the fact, I should say, that the square root was really the thing holding me back up here. If that square root wasn't there, we could have done this guy, and I should say right here. That's not our possible step right there, right? So the conjugate, I think, was not a dumb idea right there. Whenever I see a plus or a minus with a root term that I don't want to be there, conjugates are, in general, a smart way to rationalize the denominator, and we did. We got rid of the root on the bottom. But the root then being on top was still something that was prohibitive enough that we couldn't proceed on with it still being there. So my motivation to make this slightly weirder u sub that I made right here was recognizing that the one thing holding me back in my previous attempt was the square root. So I said, fine, let's get rid of the whole dang square root with the u sub right here. It led me to have to do a little bit funkier substitution steps, but these are ones that we're a little bit more comfortable with now that we've seen the trig things, where we've sort of flipped our substitution inside out, where rather than plugging in just simply u for a whole expression of x, we plugged in a whole expression for u in for just an x right there, just like it happens in our trig subs, and it led us to a place where we could actually make this guy happen here. So let's go ahead and do the partial fraction decomposition. We're pretty good at it by now. Make this guy happen here. So here we are. So u over u minus 2, u plus 1 equals a over u minus 2 plus b over u plus 1, right? We just need linear, just constant factors on top because they're both linear terms. I'm going to clear fractions by multiplying by the entire denominator on the left. A will cancel the a term will cancel the u minus 2, but it'll keep the u plus 1. B will cancel the u plus 1, and it'll get hit with the u minus 2. I'm going to expand. I'm going to group by powers of u. And by the way, notice these parentheses I'm using right there. Totally not necessary. Totally a good idea for you to help remind yourself that that is collectively your constant term. And that's going to be helpful for me over here when I recognize I have no constants on the left. I only have u's. So it looks to me like there is one copy of u on the left. There are a plus b copies of u on the right. There are 0 constants on the left. There is a minus 2b constants on the right. So I've got my system of 2 equations that I can now solve. It looks like A is the same thing as 2B, and that's going to lead me to say 1 equals 2B plus B, and therefore 3B equals 1, B is equal to 1/3, and that's going to allow me to say A is 2 times B, so it looks like A is going to be 2/3. So now I have a way to rewrite my fraction here, my fractions. So now it looks like we're going to get here, yep, and that 2 is sitting out front. It looks like this is now 2 times the integral of A was 2/3. So A is 2/3 over U minus 2, plus B was 1/3, and that's over the U plus 1. I can now do my integration. It looks like I'm going to be getting 4/3 is the constant associated with the first one, times the natural log of U minus 2. It looks like 2/3 is the coefficient on the second one. 2 times 1/3 is 2/3 times the natural log of U plus 1 plus C. And we're basically done. I just want to rewrite it in terms of X. What was my substitution? U was square root of X plus 2. All right. All good there. And we've got ourselves a final answer. It certainly looks like, when I see those fractional coefficients sitting out front, that's definitely me saying, man, I don't want to combine those natural logs and get a whole bunch of fractional powers in there. It's not necessarily going to be any cleaner. I think that's a good final format for us right there. Cool. So let's look at one more one real quick here. We'll call it a day. I just want to show you guys more stuff that can happen when we end up in these fraction situations right here, and we'll be all good right here. So next one coming up here. I know that this is probably making some of you upset to continue to see some trig things out here. That's good. Let's use your anger right here. So when I see cosine over sine squared plus sine as an integral right here, this doesn't quite feel to me like the trig things that we saw in 7.2 and in 7.3, because this feels to me like that sum is a huge issue for me, right? The whole thing about all the stuff that we learned in 7.2 and 7.3 is we want to heavily take advantage of our trig identities, right? And so I feel like I think things like, do I want to do something like factoring out a sine? Ugh. I verbalize all these things as just like sine instead of sine of x, and then sometimes I try and write them that way, and that's not cool. Sine x plus 1. Is this something that I want to do? I don't know. I don't know any identity for simply sine of x plus 1. So that doesn't necessarily seem like a route that I want to go. Other things I could think to myself are, every time in my life I see a sine squared, I'm like, ooh, I know what sine squared is. Sine squared, that's really 1 minus cosine squared, right? But mixed powers of sine and cosine is not a great thing for us to be dealing with here, right? Now, the thing that I am kind of seeing out here, though, is this feels to me like our integrand is like wanting to be a rational function, but it's not quite there. And I want to help push it over that edge. So I'm thinking to myself, can I just I'm expecting that all of you guys are just exhausted by trigonometry at this point, and so I'm saying, and again, use your anger to motivate your math, right? If you're upset about how much trig you've done in the last week, good. Can we like eliminate trig from this integrand here? I think that the answer is yes. I think that if we are careful with a little bit of a selection here of how to get rid of our trig terms, maybe we could do that, right? So here's the thing that I'm thinking. What if we did a u sub? If I picked u to be sine, then du is going to be cosine x dx. And look what we end up getting here. It looks like we're going to end up getting cosine x dx. That's just du. And it looks like in the denominator, we're going to get a u squared plus u. Right? So this is what I would call a function being rational in form. It's not a rational function because it's got trig stuff in it, but it is in the format of something that is rational right there. And I can use my u sub stick right here, and I can force this thing to actually be in that form here. So this looks like something I can easily do partial fraction decomposition on. U times u plus 1. Let's see how fast we can do this guy here. So I decomposed it. I found a to be 1 and b to be negative 1. So I can rewrite this guy as 1 over u minus 1 over u plus 1. That was easy. The integral is easy. All I got to do is sub back in some terms for u. What did we choose u to be originally? U was sine of x. And by the way, maybe before I do this one, before I sub back in, while we're still algebraic and not trigonometric, maybe this is a good place for us to do our combining of the natural logs here, and then getting for our final answer, natural log of sine x over sine x plus 1. Cool. Nice and quick one right there. It's about as quick as our partial fraction decomposition will ever get. So this is one of those things with partial fraction decomposition. I know it's a little bit weird. This matching coefficients idea takes a little bit of getting used to, but once you're quick with it, it's quick. And you end up with a lot of relatively simple equations to solve here. Very, very common that one of them is just straight up claimed for you. It's not like you're going to get 4 unknowns with 4 equations where all 4 unknowns show up in every equation, right? Most of the equations have 2 or even just 1 of the unknown, like a equals 1 did right there. Makes solving really, really easy for this guy right here. This is rational in form, and so seeing the factored form right here felt to me like it could almost be partial fraction decomposition. We u-subbed it to make the numerator and denominator each polynomials so that we made this guy happen with a u-sub and a partial fraction decomposition. So as my last one for you guys today, if you want to see one that's like that, then you should go ahead and attempt this guy right here. The integral of e to the 2x divided by e to the 2x plus 3e to the x plus 2 dx. You should notice that that denominator should absolutely look like a quadratic to you. And don't forget that things like e to the 2x, that's the same thing as e to the x squared. That's kind of like your one guiding hint on this guy right here. And so using kind of the same idea as up above, we can make a substitution to turn this this is a rational in form function. It's not a rational function, but it's got the structure of a rational function here. By making a single u sub, you can turn this into a rational function, and you can do your integration by parts. Integration by parts. Partial fraction decomposition. I was thinking of the other form that's a 8-syllable technique name right there. Do the integration, sub back in, and you're going to be good to go. So go ahead and check out this one. There will be 1 or 2 in the homework that feel like this trig one, like this exponential one right here. And it's not too bad. It's just adding in 1 extra easy layer of an easy u sub, and you've got it there. So that's it for me today for 7.4. We're going to hit 7.5, general strategies for integration. 7.5, we're not going to see anything new. We're just going to talk about, let's talk about why has this been so hard for the last few weeks. And let's talk about some strategies that we can form to help us understand when should we recognize things as easy, when should we recognize things as hard, when should we recognize things as impossible. And when things are hard, what should be our checklist of things that we should look through to find our things of interest out there? Why does it seem sometimes harder to solve these when there's a constant in the numerator rather than an expression? So that's a good question right there. So I'm going to scroll back up to the very top example and answer your question right here. And I think that my kind of motivation to my answer to your question is because I want to do these U subs. This would be the easiest thing that I could ever do right there, right? So I'm thinking to myself that like if I had 2x plus 3 in the numerator, then this becomes what we did literally on day one of this class all of a sudden right there. So I would say my answer to you is when we have quadratics in the denominator down here, our best case scenario is a linear in the numerator because that means that a u and a du are 1 degree off from another, and that's best case scenario for us. When we go from having quadratic to constant, that's a 2 degree difference. It is not gapped by one single derivative anymore, and therefore we have to do the partial fraction decomposition. So I like your question because what your question is sort of getting at is kind of the stuff that we're going to talk about in 7.5, which is kind of saying like, how do we recognize easy cases and how do we recognize hard cases? And so this is saying like, don't forget what happened with U sub. You were looking for an expression and its derivative or a constant multiple of its derivative. And so combining a quadratic with a linear helps us get there. A quadratic and a constant is too far separated, and so we have to have a special technique like this one right there. So that's a good question, and that's the exact type of stuff that we want to be discussing in our next video here for 7.5 is saying, why do these seem easy? Why do these seem hard? And we're going to look at some that are closely related to each other and see which ones are doable and which ones aren't, and kind of feel that out. And like, oh, what are broad things? Like, if we're to sum up what we've learned in the last couple sections here, in the last couple chapters, it's integration is hard, and it's not straightforward as to how and why it's hard. Some that look hard are easy, and some that look easy are hard, and it's like, integration's weird like that, right? It's really not obvious what should be the easy stuff and what should be the hard stuff. And so that's why integration is such like a classic math challenge, I think, is because nobody ever just gets to the point where they're like, oh yeah, I can do all of these. It's man, you learn one thing, you forget one thing, and so the number of integrals you can perform is the same. It's like that generally seems to be how that goes. So we'll kind of summarize a bunch of that in 7.5. But very good question right there. It's a completely reasonable thing to be asking. So yeah. Good. Let's keep those thoughts rolling here. And I will see you guys in the next video for some general strategies. And actually, by the way, I'll say as my last sentence here, finishing up chapter 7, what we're going to do is we're going to motivate our final sort of monster chapter of this class, which is chapter 11, which has 12 sections in it. And it's not going to have hardly any integration in it whatsoever. But we are going to start thinking more about infinity. And you should notice that one thing that we've never done with integrals is have infinity as a bound of integration. That's one of the big important topics that we still have to discuss in chapter 7. Chapter 8 is an awesome chapter. We get a ton of more applications of integration that are all really, really cool. So I really like chapter 8. We'll get a little bit of stuff with parametric and polar before we then move on to our beefy last third of the semester, which is our chapter 11 stuff out there. So I'll see you guys for strategies for integration in the next video. Have a good one, everybody.